In aviation, the engine isn't just another subsystem. It's the single biggest bottleneck that decides whether an aircraft flies, when it enters service, and if it ever gets certified. After Western sanctions cut Russia off from GE Rolls-Royce, and Safran engine dependence became a strategic vulnerability. In that context, PD-35 isn't just a new engine. It's a platform meant to unlock wide-body aviation at home. So why does it matter so much? And how could an engine platform reshape Russia's aviation future? Let's discover. If you want to understand PD-35, the first thing you have to forget is the idea of an engine as a one-off product. It was never meant to be a standalone power plant built for a single airplane. It was conceived as a technology platform, and that distinction changes everything. The program is led by United Engine Corporation, and its roots go directly back to PD-14, the engine developed for the MC-21. That matters because this engine is not a clean-sheet fantasy or a political announcement disguised as engineering. It is an expansion of a core that already exists, already runs, and has already forced Russia to solve real problems in materials cooling and digital control. This is how serious engine families are built in the real world. In commercial aviation, no country sustains wide-body aircraft programs by designing a new engine every time. GE didn't reinvent itself for each airplane. The GE90 led to Gen X, which informed later derivatives. Rolls-Royce didn't build isolated engines either. The Trent family is a modular ecosystem scaled, tuned, and adapted across decades. That's the industry logic PD-35 is following. The goal isn't to win on headline performance. The goal is to establish a reusable high-thrust core that can support multiple wide-body aircraft over a long industrial timeline. This is why the engine exists at all. Without a domestic engine platform, in the 30 to 35-ton thrust-class wide-body aviation simply cannot exist as a sovereign capability. You can design airframes, you can build wings, you can even assemble prototypes. But without an engine family, you control every wide-body program becomes fragile, temporary, and politically exposed. That's not theory, that's history. After sanctions, Russia lost access not just to Western engines, but to updates, spares, and certification pathways. Engine dependence stopped being a commercial inconvenience and became a structural risk. It is meant to remove that risk by creating a foundation, not a single solution. The platform is designed to generate a family of large turbofans adaptable to different aircraft weights, missions, and ranges. This opens the door to twin-engine widebodies, where four-engine layouts once dominated. Not because it's trendy, but because economics and fuel efficiency demand it. More importantly, it allows future aircraft programs to be defined around an existing propulsion ecosystem rather than waiting for an engine that may never arrive. The PD-14 connection is what keeps this grounded. PD-35 builds on the same design philosophy, the same digital control concepts, and much of the same manufacturing logic, but scaled and reinforced for a completely different thrust class. That scaling challenge is enormous, and no one in the industry underestimates it. But it's also the only credible way to move forward. Engine platforms are built step by step, not declared into existence. This is why it should be viewed less as a product announcement and more as an industrial pivot. It signals a shift from aircraft-first thinking to ecosystem-first thinking. From designing airplanes and hoping engines follow to building a propulsion backbone that future aircraft can rely on. If Russia wants wide-body aviation that survives beyond prototypes and politics, this is the only path that makes sense. And that's what makes this engine more than just another engine program. If PD-35 is the platform, then the real battle happens deep inside the engine, far from spec sheets and marketing claims. This is where most engine programs quietly succeed or fail. It sits in the 35,000 kilogram force thrust class, roughly 340 to 350 kilonewtons, placing it squarely in the wide-body twin-engine category. It is not designed to compete with ultra-high thrust engines like those on the A380 or 777-9. That choice is deliberate because it defines the engineering philosophy balance, not brute force. At the center of the engine is its high-pressure core, where almost all technical risk lives. This core is an evolution of PD-14 expanded and pushed harder rather than redesigned from scratch. Russian engineers added an extra high-pressure compressor stage and targeted a higher overall pressure ratio. The challenge here isn't chasing a headline efficiency number. It's extracting more thermal energy from the same airflow without sacrificing durability. That balance between pressure, temperature, and lifespan is the real engine war. Temperature is the next battleground. Modern turbofans are defined by how hot they can run. Before the turbine fails, pure physics, not marketing. PD-35 is designed for turbine inlet temperatures approaching 2,000 degrees Celsius, placing it firmly in the fifth-generation engine class. To survive that environment, it relies on single-crystal turbine blades and advanced internal cooling channels that route air through microscopic passages inside the metal. These are threshold technologies. They separate modern engines from everything that came before. And this is the line most engine programs never cross. Not because they lack ambition, but because physics, materials, and time don't negotiate. What often gets missed is how rare this capability actually is. Globally, only a small share of engines combine high-pressure ratios, extreme turbine temperatures, and acceptable long-term durability, roughly 15% by industry estimates. That context matters. It isn't catching up to 1990s designs. It's attempting to enter the same technical tier occupied by today's most advanced wide-body engines. The fan system reflects the same restraint. With a fan diameter of roughly 3 meters, it prioritizes bypass efficiency and noise control over headline thrust. Its length and mass are sized to integrate into modern twin-engine widebodies without forcing radical airframe compromises. This is not under-ambition, it's disciplined engineering. Across the core design, the pattern is consistent. There are no miracle claims, no sudden performance leaps. What it shows instead is a willingness to engage the hardest parts of engine physics, where progress is slow, expensive, and unforgiving. That's where engine programs earn credibility or lose it forever. The engine's core makes one thing clear: Russia isn't trying to shortcut the fight. They're choosing to fight the real one. The most important shift inside PD-35 has nothing to do with thrust or efficiency. It's manufacturing, and more specifically, how Russia builds engines under constraint. It's manufacturing. Not what the engine promises to deliver, but how it's actually built. Because after sanctions, the real constraint wasn't just missing components, it was missing methods. Additive manufacturing sits at the center of that shift. It integrates 3D printing into critical engine parts, including low-pressure turbine elements and exhaust components. These aren't cosmetic pieces. They operate under extreme heat stress and fatigue over tens of thousands of cycles. What makes additive manufacturing decisive here isn't novelty, it's geometry. Traditional machining forces engineers to simplify designs around tooling limits. Additive manufacturing reverses that logic. Engineers define airflow paths, cooling channels, and load structures first, then build them layer by layer. That approach unlocks multiple advantages at once. Weight comes down, cooling efficiency improves, production timelines shrink, and just as importantly, dependence on foreign tooling ecosystems drops sharply. Once a design is validated, production becomes largely software-driven. That's a structural increase in industrial resilience, not a marginal efficiency tweak. Composite fan blades tell a similar story. The engine moves away from all-metal fan technology toward polymer composite blades reinforced with carbon fiber. The result is roughly a 30% reduction in blade weight, lowering rotational inertia, and improving fuel burn and throttle response. It also reduces stress on hubs and bearings. But the bigger shift is industrial. This requires large-scale composite manufacturing, a capability Russia historically lacked in civil aero engines. It forces that capability into the domestic supply chain. Taken together, these changes point to something deeper. Engine manufacturing is moving away from heavy metallurgy-first thinking toward digital production, modular architectures, and data-driven iteration. Components are no longer optimized in isolation. They're designed as part of a system that can evolve. That's why PD-35 isn't just a new engine. It represents a reset in how engines are designed, built, and sustained. And that manufacturing shift, not headline performance, is what truly makes it matter. If you're interested in how aircraft programs succeed or fail behind the scenes through engine supply chains and long-term industrial strategy, consider subscribing. That's what we analyze here. PD-35's real impact only becomes clear when we separate what it actually changes from what it deliberately does not. Because this program isn't trying to win every battle in global aviation. It's trying to unlock one very specific capability Russia has lacked for decades. What it does change is structural. For the first time, Russia has a credible path toward a domestically powered wide-body twin-engine aircraft. That alone reshapes internal design logic. Four engine layouts like the legacy IL-96 were never about preference. They were about necessity. The engine enables a move away from redundancy for survival toward efficiency by design. That opens the door to more competitive fuel, burn, lower maintenance complexity, and realistic long-haul operations inside Russia's own network. It also creates an engine foundation that can support future wide-body projects, including portions of CR929, without being hostage to external suppliers. Just as important, PD-35 changes timelines thinking. This isn't a stopgap engine meant to plug a short-term hole. It's a long-horizon investment in propulsion capability materials, manufacturing, testing, certification that compounds over decades. Engine programs don't pay off quickly. They pay off persistently. What it does not change is the global balance of power. It is not designed to outperform GE or Rolls-Royce in open market competition. It is not optimized for ultra-long-range Western wide-bodies. It is not being positioned as a mass export product. This is a strategic engine, not a commercial challenger. That distinction matters because it defines success correctly. The timeline reinforces that reality. Original production targets around 2028 have shifted closer to 2030, largely due to prioritization of PD-14 and PD-8. That isn't a collapse. It's resource allocation. Engine development at this scale is brutally sequential. You don't rush the core. In the end, PD-35 doesn't rewrite aviation overnight. What it does is far more consequential. It redraws the boundary of what Russia can build independently. And in an industry where engines define freedom of design, that boundary is where the future starts. So here's the real question. Do you see PD-35 as the foundation of a sustainable wide-body ecosystem, or as a necessary but limited stopgap? I'm curious how you see it.